All right. Hi. Today we're joined by Shashwat Shukla. He's a PhD student at Columbia University. He's pursuing computational neuroscience. Thank you, Shashwat, so much for joining us.
Thank you for having me, Harush.
Would you like to introduce yourself?
Yeah, sure, I can do that. So, I studied electrical engineering and computer science at IIT Bombay for my undergrad. Started off as a physicist and then sort of moved into ECS and all that. And then I'm now a PhD student at Columbia University in the Bionet lab. We're a lab that studies the fruit fly brain. So I'm getting my PhD in what the department calls neuroengineering. And yeah.
All right. Okay. Wow. Uh, so computational neuroscience does form like the basis of what you study, or like how does it work exactly?
Yeah, right. So, in a sense, like if you think of it as a field that can draw on tools from any other field, the objective of our lab is definitely to understand brains. So, in that sense, we're doing neuroscience and we use computational models and tools to understand. So, that's why it's computational neuroscience. But, like, in terms of positioning and funding and things like that, we're still in the electrical engineering department in Columbia, and then a lot of our tools do in fact come from fields like signal processing and traditional, let's say, E and CS fields. So
Hi, hi. Thank you. That's a really good. I think a lot of people have difficulties understanding the structuring, especially when it comes to the
yeah,
intersection of biology and engineering, especially electrical engineering. So thank you. Like
right.
that was quite detailed. So diving straight into the questions, how would you explain your research interests to someone with a STEM background versus someone who's just a high school student right now?
Right. So, as you said, because this is always a fuzzy area, and because neuroscience itself is both a very big and complex field and one that's in many ways still very nascent, it becomes difficult to kind of just give one answer to this question. So, I kind of thought of breaking it down in terms of like an answer for each letter of the word STEM. So if I were talking to a scientist for S, I would tell them that I'm trying to understand how the fruit fly brain works. So the formal way of saying this would be I'm trying to reverse engineer the functional logic of the fruit fly brain. So I'm interested in how it works, right? And if I were talking to someone who's more inclined towards technology and engineering and wants to know what good this is all for, the scientific curiosity aside, I would say, hey, at some point in the future, maybe 10 years, maybe 20 years from now, when we want to build really miniaturized drones that fly around, are energy efficient and whatnot, we'd want to emulate something like an insect. And that's why we're trying to understand the mechanistic functioning of a small little insect. And for the mathematicians, my initial motivations as a primarily theoretically and computationally driven person come from the mathematical and philosophical mysteries here as well. I would say that I'm very interested in the representations of various things that we would correlate with behavior, perception, and things like that. So I want to understand how neural codes are represented in the fly's brain and how they're computed upon to do various interesting things. So that's my answer for the STEM, folks. And now that we have a lot of this jargon out of the way, I can give a sort of more story driven, let's say, answer for everyone that's sort of, curious about all this. So to the high school students, I would say, and this is in fact also specific paper recommendations for everyone, including high school students and anyone that's interested. There's a really nice paper out there called Can a Biologist Fix a Radio? And then that inspired another paper that's called Can a Neuroscientist Understand a Microprocessor? So let's start with the radio analogy first. So fairly simple, like you're a little kid, you're growing up, with your parents' radio. Maybe it's an iPhone now, but whatever it is, it's a complex device, and you can see that it has some like higher level input output functions. You click on something, something happens. You break it apart, and then you see that inside there are a bunch of components. So the analogy here is that a biologist would open up a cell or a brain, and you would see different constituent parts like a neuron, a synapse, and whatnot, and you can then classify them based on what they look like, right? So that would be an anatomist saying these two neurons look similar. So you can label the boxes as red, 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 blue, 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 and then you have this giant puzzle now, and you're trying to reverse engineer what these different boxes do. So that's why it's a reverse engineering question. And so if you are in double E and you're like competing with Intel to make a better chip than they do, you would also be doing just this with the goal of like beating your competitors out. You're trying to reverse engineer what it does, right? So you don't have the same sort of let's say there's no fixed goal per se, and that's also something that I find very interesting. So we can talk about that too.
Yeah. Wow. Okay. So point is to the way that you put it, right? So it's essentially reverse engineering a particular system. In the
Right.
case of a biologist, it's reverse engineering the system that constitutes a living being,
Yeah.
right? And in electrical engineering, you build very complex systems out of scratch in some sense or the other.
Right. Yeah.
But then it turns out that to a great extent, like the systems that have been sort of developed by electrical engineers have been inspired to a great extent, especially in computational, engineering by like biological systems.
Right.
So in like you can sort of draw parallels in, how you've comprehended that system to build a new system and then sort of apply the same logic in the reverse direction. Would that be like an addition? Like would that be an accurate addition to what you said?
Right. Yeah. No. In many ways, that's a very good line of reasoning, and so in the sense that like if you know some electrical engineering, you could apply those ideas to like try and understand or guess what the function is. And I'll build on that and also say that when conceptually thinking about the difference between neuroscience and electrical engineering, what I both love and perhaps admire so much about engineering as a field and a goal is that you have first principles defined. Like
Yeah.
you know what a transistor does, you know what a
Yeah.
wire does, you have models for every single thing that you wire up together. So in this case, when you are trying to reverse engineer things, you don't even know what you're trying to reverse engineer.
Yeah.
So
Yeah.
there's another layer of unknown. So like
Yes.
I guess at a philosophical level, I would
Yeah.
describe it this way: engineering is about solving for known unknown
Known.
quantities,
Yeah.
whereas science is about unknown unknowns, and like
Yeah.
it's
Yeah. Wow, that is really insightful. Yeah, like in biology, you're trying to essentially model things which you don't even know if they exist.
Right.
As in, like you're modeling something, but there are tons of different things that you don't know about. So it's like a best guess thing till you actually reach the end result, which might be like a holistic model of the
Yes.
entire thing. Yeah.
Right.
Wow, thank
Yeah.
you for that. That's a really insightful answer. So my next question is, what was it that initially sparked your interest in your current research, and how did you recognize it as a career pursuit?
Right. So I've always been sort of curious about yeah, information theory, and I was kind of going down the route of trying to understand what it's good for, semantically speaking, let's say, by interning in a computer vision lab. So I did that in the second year of college, and then we were working on a pretty interesting problem, which is action localization in videos. So the lab had designed this really interesting two-stream deep neural network, and I, as an undergraduate, was given the task of training it on some data, trying to understand when it works and when it doesn't, and so on and so forth. And I learned so much about machine learning and the current approaches to computer vision. This is maybe 2015, 16, and I learned a lot, but I also came away feeling like the word neural network is maybe a bit, I guess, I don't know, overemphasized in how close it is to actual neurons. And I kept
Yeah.
asking questions about all right, is this how real brains work? And I didn't get any satisfying answers. It felt like I'd found a rabbit hole with like no answers, and that really piqued my interest. And the more I read about real neurons, I realized that there are specific properties of real neurons that are not being both modeled and potentially exploited with the current simplified or oversimplified models for neurons in these networks. So that's where it began. Um,
Yeah, yeah. Wow, that's amazing. So I'd just like to connect this to,
yeah.
you know, something that, or maybe I'll just give you the chance to answer it because you probably already know what I'm referring to. So,
Uh-huh.
what's the most exciting aspect of your research for you?
Right. Yeah. So I can perhaps continue along this line of the conversation to answer. So, when I was reading up on real neurons and like real neural circuits and how it's all composed together to make a brain, so many aspects from many disciplines of science and engineering all sort of immediately pop out at you. Like, if you're an electrical engineer and you're looking at these like really fancy FinFETs, which are like these 3D chips now, and you're like really impressed by the 3D topology of these circuits. The brain is literally a three-dimensional electrochemical circuit. So just in terms of engineering scope, brains are like already so much better at what they do. You have nanoscale transistors, they're called synapses. They're both electrical and chemical, controlled by genetic information as well. So just the complexity of all of it, and just how interdisciplinary it was, just how many roads all lead away and towards this field that we call neuroscience was really exciting to me. I went to college and felt that like there are all these like artificial divisions between departments, and everyone's all like in their own camp trying to sort of understand why my field is so important. I think neuroscience for me unifies all of it together towards a greater, incredibly complex goal. And we were talking about some unknown unknowns, and for me, this is always personal preference. For me, I like that there is a lot of unknown unknowns. It can be incredibly frustrating. You don't know what you're doing, quite literally, but I think there's some artistic beauty there. So I really love that aspect of neuroscience as well. It's a renaissance field,
Ye-
so to speak, in a way. So,
Yeah, yeah. Um, would you like to talk more about that bit?
yeah, sure. Absolutely. I mean, like I said, I kind of got into all of this starting as a physicist because I wanted to understand, like every physicist does, how do atoms and like all of these build up to everything that we see. For me, a light bulb moment also was that there is a certain limitation to our own physics modeling capabilities in the brain. Like it's an inversion of that logic to say that every thought, every idea, every feeling, your taste in music, everything is somehow contained within trillions of neurons. And like
Yeah.
I kind of think of it as astrophysicists staring out at the sky with trillions of stars out there. There are trillions of little stars in your own brain that somehow capture some of that beauty, So I kind of fell in love with that inversion as well, and it's there's just so many infinitely
Yeah.
many questions to ask in that regard as well. So
Right.
yeah.
Right. Um, okay, so you know, con- sort of continuing on that line and sort of narrowing it down,
Yeah.
like you've obviously like very beautifully captured like the broadest possible set of interests, like set of
Sure.
explanation for your interests you
Yeah.
can have.
Ah.
But if you were to sort of talk about just one research idea that was sort of pivotal in shaping your current passion for your research, what might that be?
Right, right. So I'll provide some more context for what I'm doing, and maybe along the way I can tell you a story that also underscores just how interdisciplinary all of this can get. So I am specifically studying fruit fly connectomes. So what a connectome is basically a 3D wiring diagram for the brain. So if again I use the analogy of a microprocessor, if you're trying to reverse engineer it, you will take out the outer covering. You do that with the fly's head as well, and then you would scan it. typically using an electron microscope, which is precisely what they used for the fly brain as well. So, and then you would try and look at all the wires and figure out what's going on. So, in the context of the fly, they take the fly's brain, they slice it up like salami, and then scan each piece, and then they digitally reconstruct all of that to get a 3D map out. So, you're looking at this giant, complicated 3D wiring diagram, and you're trying to figure out what it does. So, one of the early examples of something interesting coming out of this was when people discovered a compass in the middle of the fruit fly's brain. So this compass literally looks like a donut. It's called the ellipsoid body. It is a truly beautiful neural circuit that literally looks like a donut, and it's formed by a bunch of neurons that have all arranged themselves geometrically in that shape. And that for me was just such a beautiful convergence of geometry slash topology and nonlinear dynamics with sort of this kind of circuit based modeling. So in the past I'd worked a lot with spiking neural networks. I'd modeled C elegans circuits and a bunch of other things, but this sort of detailed neuron synapse resolution modeling of neural circuits with a specific structure to them really captured my inspiration. I really wanted to work on that. And I can go a bit further with this story because what I'm also doing now is trying to specifically study small parts of this connectome. So our lab studies how the fly smells things, how it sees things, and so on. So with regards to how the fly sees things, we all know that fruit flies and flies in general have these compound eyes with a bunch of these little hexagonal tiles. They're called ommatidia. So what recently happened, and I just cannot I just love the story so much because someone so there's a bunch of neuroscientists who had a hunch that there's more going on with these little ommatidia. So what they did is they took a small fruit fly, put it in a particle accelerator in Europe. I think it's in France somewhere, and they shot a bunch of high speed, essentially X-ray particles at the eye of this fly, and the retina of the fly obviously burnt out after a while. But what they did find is that these high energy particles make the photoreceptors, which are like neurons inside the fly's eye, actually twitch around like this. So they actually found what are called microsaccadic tremors inside the fly's eye, and they imaged that, of course, using various other techniques. And so put together, this was a physicist approach to understanding things, literally smash particles into an eye. And then I'm studying how microsaccades can also help with the vision of the fruit fly. And then at the end it all leads into the compass, because the compass is also governed by the visual inputs that it receives. So
I see.
It all literally converges also onto some circuits that are
I see. So, was there any significant conclusion that could be drawn from the twitching of the microcircadia? Is that what's
right? Yeah, microsaccades, right. In a series of very interesting papers, some of our collaborators have also found that not only is it just that these microsaccades happen, this is always the question in biology, is this just a feature with no function per se, or is there some specific function that you can point to? So with microsaccades, what they found is that the two eyes of the fruit fly, they saccade sort of in tandem, and they do sweeps like this. And when they converge in the middle, because you have two rays of light converging somewhere, you can do depth perception using that. So what they found is that fruit flies actually see things with depth. And also that these ommatidia, they're really big, right? So you'd imagine the fly sees really low resolution stuff. So what they also found is that flies can actually detect objects like small dots, which are smaller than the size of these ommatidia as well. So that would be called hyper resolution. So there's a bunch of stuff happening with all of this, which I think is
It's quite interesting. Wow. Okay. So obviously, I'm not a neuroscientist, so I'm probably not able to appreciate the extent of how significant this is in terms of scientific discovery. So I'm obviously fascinated by whatever you told me, but I
Right.
think my vision is a bit myopic in that sense. I'm not able to
Yeah.
see the complete picture. So I do apologize for that. I haven't
No worries.
trained
No,
as
of course, it's fine.
a yeah. I mean, I'd just like to introduce like a light note on that. Is that any subject is sufficiently fascinating once you know, two conditions to be satisfied. Like you have like a great teacher, like who can inspire you to sort of walk in that direction, and second, you have
Yeah.
some, background knowledge to be able to understand what the professor is
Yeah.
saying.
Right. Yeah.
So
Yes.
the first condition is obviously there. The second, not so much. So, okay. So moving on, what are some common misconceptions about your research that you would like to talk about and address? Um, yeah, like how would you like to
Right.
address some common misconceptions about research?
Yeah, like I guess among the assorted set of like questions that I get about what we're doing and so on, I definitely would like to talk first about yeah some of these ideas that I just did because I think if you don't know all of this a priori, a fly is a fly. It's a small insect that you try and swat if it annoys you too much. So the inherent complexity of a brain that's the size of a pinhead, quite literally, is sometimes really difficult to appreciate. And I have had my mind blown almost on a daily basis staring at this connectome. And so, one of the common misconceptions is that foo fly brains are somehow like too simple to be relevant in terms of like how all of this would generalize to like rats and humans and like there are all kinds of questions that somehow become anthropomorphized a lot like okay, can only humans perceive objects, for example? Do every other small insects just see patterns? Is there
Yeah.
sort of higher order processing? What's going on with all of that? So what we definitely clearly see both in terms of the kinds of brain regions that the fly has and in terms of the experiments done on object processing and so on, the fly can definitely perceive at least basic shapes. So that in itself is quite exciting. And I would also like to maybe clarify the goal of some of this research because people, especially with a STEM, maybe let's say an engineering background, may not sometimes, see the fly and what we're doing in the same light. Where if you have a very hardcore engineering goal in mind, a lot of research into say what a single synapse does or what a single neuron does seems to pale in comparison to when you can stack billions of like let's say albeit simple neurons together to do very impressive things. Like I must get in a few digs at AI while I can before AGI is discovered, so I'm going to take that opportunity.
Please do.
And I kind of, have always been very irked by the direction in which AI has taken in recent years, and that it's incredibly impressive. I mean, it is like magic, and that's kind of also the problem. It's a little bit too much like magic. It would be like,
Yeah.
I guess in a way, an analogy would be that you have a supercar, but if you open the hood, you don't know how to fix your own car, and that deeply concerns me. And which is why I've definitely been very passionate about sort of continuing on this line of trying to build more rigorous models, just be humble and understand maybe 10 neurons and what they do. So that's kind of what our lab also kind of believes in. And there's still a lot to be discovered about just individual neurons. So yeah, I find all that quite interesting.
Definitely. So I'd just like to raise a question here. I mean, this relates back to
Sure.
um, some sort of like a paradigm of modeling you'd introduced before, but like this particular question has intrigued me for a long time. Well, not
Sure.
the question is basically, can you model a single neuron? Like maybe you can model a single neuron using an electrical circuit, but you can't model multiple neurons using electrical circuits for some reason.
Right. Yeah, so that's a great question, and also one that um, has big question marks at every spatial scale of this question because, yeah, like you said, like if you had a good electrical model for one neuron, you should be able to combine it with other models to build a systems level electrical model. So the devil literally seems to be in the details with all of this. And what definitely ends up happening, one is that lots of small non-linearities mess up a lot of this modeling. Like the simplest possible model for neurons, electrically speaking, which experimental neuroscientists still use with good reason, is one where the membrane of the neuron is a capacitor, so it holds
Yeah.
voltage, and then you have sort of if you do some double E, you will see all these like cable models.
Yeah,
So
yeah.
how signals propagate on linear cables, you can do that as well. You can then sort of couple it with resistors to model leak. You can add in a few diodes to model directionality. You can keep going indefinitely. It may just be that a lot of this is a matter of scaling these models up, much like with ANNs and just a simple ReLU function. It seems to work, and it's all you really need. So it's hard to argue either way for like what the minimal computing unit you require is. And this is something that has also been a question that I've been very curious about. But I will say that now, having sort of seen real neurons a lot, I would also sort of go further and sort of say that it may not be that you need anything more than a simple non-linearity like ReLU, but it's also a matter of like how you organize and optimize for the architecture of your system. So it'd be like saying we've been getting much better computers over the past 10 years, not just because you have smaller and smaller transistors, but we found better ways of caching, we found smarter ways of routing signals and whatnot. So even with individual neurons, even if each synapse, which is the smallest unit that we think of right now in terms of function, is just a simple nonlinear function, let's say, and you can pick one, and you have to compose all of those together, what we're finding is that there are some very interesting nonlinearities at the end of a dendrite, which is the input region, which then makes it so that you could model all of this by adding up nonlinearities, but in some sort of scale emergence sense, you would
Yeah.
rather model it as something else. So biology is full of these like messy abstractions, and the question is, what level of abstraction do you even use for a single neuron? So I've had a lot of my old opinions updated by looking at the connectome, because what
Yeah.
we find is that there's a lot of interesting geometric and topological structure even at the resolution of single synapses. So
Yeah.
can you imagine computing with just a few synapses and then all the wires connect these things up? So then you'd be doing more chemical computing. You wouldn't be relying so much on electrical signals propagating everywhere.
Yeah.
You compute things locally and then send them off where they need to.
Yeah.
There are in fact a lot of other things happening, like they recently discovered that in the central complex near the compass that I was telling you about, there are neurons that transmit signals not using just sodium channels but also calcium channels. So there's some kind
Yeah.
of dual coding happening. There's a lot of these things that, yes, you could pull them apart and just say that, yeah, each one is simple by itself. But I think, I'm happy that maybe my thought process is moved past just looking for the magic function to sort of ask, okay, but how is it all organized and how does that orchestra sound
Yeah.
together? So
Yeah, yeah, yeah.
yeah.
Yeah, like sometimes when you superpose two, like you said, calcium channels and sodium channels, maybe the
Right.
the compounding effect doesn't add up in a way that you'd expect it to. So maybe there's some kind of emergent behavior entering the chat over there. Like, okay, yeah, this is just
Right.
maybe it's not, maybe it's entering in a way that perhaps is not, it can't be modeled using just a simple nonlinear function. So I was in this one particular workshop where they were discussing some sort of effects between action potentials and, like, let's say there's a neural circuit in a particular region of, I think it was fruit flies only. I think they were looking at fruit flies brains using a microscope. Maybe it was fruit flies, or maybe it was. My apologies. I think they were mice, not fruit flies. So
Okay.
they were looking
Yeah.
at, yeah. So they were looking at the brain under a really like a really good microscope. And I think they encoded the calcium channels with some fluorescent
Yeah,
technique.
probably GCAM. Right, right.
Yeah,
Yeah,
something of
sure.
that sort. I'm spitballing, so I'm trying to recall whatever I remember. And what they said was that um, they didn't expect so many neurons to light up when they sort of perturbed one particular region. And they said that we were expecting like less than 5% of them to light up, but more than like nearly 50%
Right.
of them lit up.
Yeah.
Um, and so that was really interesting because they said that, okay, this can't just be explained using like a simple electrical modeling of the entire nervous system. And
Right.
if you just consider electrical modeling, then it seems to direct you towards some kind of non-local effects,
Yeah.
which on a macro scale is not that likely. So maybe there's something that we're missing when it comes to just like an electrical modeling
Yeah.
paradigm.
No, that makes a ton of sense. I think that's a great example also because you could reconcile those that mystery a few ways. You could, as you said, literally bake in non-linear connections, and you do in fact observe a lot of long-range neurons. But in some ways, there's more to that as well. Like something that I learned once I started studying these fruit flies is that they also use certain gases, literal gases, as messenger molecules. So nitrous
Uh,
oxide, for example, diffuses through the central part of the fly's brain, and it's a non-local effect in that electrical engineering sense. So
yeah.
th- they also discovered certain effects in I think it was hammerhead sharks and a few others where the strength of the electromagnetic fields in certain parts of the brain is so strong that it can be detected by magnetosensitive ions in other parts of the same brain. So you could have non-local communication even,
Yeah.
and that's really another example of how even the kind of research that I'm focused on right now may not be the right place to look at when you look at the macro function of the brain. Like, I'm interested in individual neurons and synapses and what they could do. Maybe that's just an implementation detail. Maybe you don't really need the synapse to be exactly the way it is for all of it to work out.
Yeah.
So that it's really all a big mystery still.
Yeah, yeah. I mean, I think the open-ended stuff sort of really gets the
Yeah.
adrenaline pumping, and you just want to, it's like that kind of thing where you won't be able to do like the entire thing, but
Uh-huh.
you still want to attempt doing it. So I think
Yeah.
I really subscribe to that sort of a framework where you're just like sitting like Doc Brown with the crazy hair, and you're just trying to, yeah, we're gonna do this entire thing. So no, I definitely resonate with that because I think part of the thrill in that is that there's no definite answer.
Right.
And I think you enjoy the journey much more than just like reaching the answer.
Very much so, very much so. And I think, yeah, as you said, on a day-to-day basis as well, the complexity and the unknowns are so high that
Yeah.
I've always sort of felt that the most exciting parts of science for me are where you're trying to also just find language to describe what you're seeing.
Yeah, that's
And
true.
so it becomes a quest to just, of course, understand what you're seeing, but also somehow, um, I don't know, make it make sense so that you can
Yes.
talk about the
Yes.
unknowns. It's
Yes.
that crazy sometimes. So
Yes. Yes.
I love
Yes.
that.
No. Yeah. No. No. I think definitely resonate with that because I think I'm segueing here a little bit, but once you're able to communicate about something that hasn't been known previously, I think that sort of gives you some sort of like a powerful feeling that, okay, there's this phenomenon where you're using like a very systems based approach and a very analytical approach to sort of literally model it in language that we communicate in daily, right? Like using verbal
Right,
language. And I think
right.
that sort of, I think that it's a bit philosophical, but like it
Sure.
gives you like power over that system. Okay, I'm able to describe it just using the language that we have used daily, not
Yeah.
just using mathematical equations, but like literally just using
Yeah.
the English language or whichever language that you like to communicate in. But like I think that's um, as a scientist, I think that gives you a very sort of powerful tool. Or
Yeah. No, definitely. I understand what you're saying, and it sort of is maybe one of those, you know, motivations that get you going, and then
yeah,
I think at some point you just see the grand complexity of these
yeah,
things, and
yeah.
you can only give up and say, all right, at least I can appreciate the view. You know, like
Exactly.
I.
Yeah. Yes.
So,
Yes. Absolutely. Absolutely. Yeah. Sorry.
yeah.
Sorry. I didn't mean to interrupt. Please
No,
go
not
on.
at all. No, no. I was just going to give an example that
Yeah.
comes
Yeah.
to mind sometimes. You know, like if you go and stare out at the ocean and you see all these waves, you can sit there for hours and the wave patterns won't repeat. And
Mm.
you can, it's probably true of brains as well that like no thought is exactly the same thought. It's a product of a nonlinear system and whatnot and what forth. So now, should the goal be to describe mathematically every single wave, or should it be to describe the simplest possible wave to get a handle on what a wave is? Do you solve Navier-Stokes equations and you're not done until you solve the Navier-Stokes equations, or are you done with a story? Like, what's the right resolution even to sort of talk about these things? And I mean, for the people who are doing medicine, these questions are very sort of practically relevant as well. Like, how do you change the system? Like, do you just throw a rock in to make a ripple? Is that good enough to fix things? Like, you know? So it's a lot we don't know.
Yeah. Yeah. Sorry. I just like to ponder over the medicine
Yeah.
analogy that you gave.
Mm-hmm.
Because over there the stakes are so like
Yeah.
they're just incredibly complex because you don't actually know
Mm-hmm.
how bad the how good or bad the
Yeah.
ripple effect may be, and
Absolutely.
just the like I think a lot in medicine is just sort of spitballing to see if it works or not. I don't think
Yeah.
their analysis is as deterministic
Mm-hmm.
as we would think
Yeah.
as a scientist perspective to be,
Yeah.
and I don't mean any sort of I don't mean to diss them in any way, but
Yeah. No, of course.
it's just that the way that medicine has evolved over the past 1,000 years,
Mm-hmm.
I think we really tend to not look at the time and effort that has gone into the trial and error sort
Yes.
of process in
Yes.
medicine to be able to, um, you know, be able to deal with as complex a system as the human body.
Absolutely. Absolutely. I completely agree. And like, I think as someone with an engineering background and someone that always sort of, you know, I grew up with sort of this hope that math would unify everything. You know, in some ways, that's the naive hope you have. Everything is conveniently sort of, and in some ways that's tautologically almost true. Like if you have the laws of physics, everything else is probably still a consequence. I don't myself at least believe in paranormal or supernatural stuff, but anyways, regardless of all of that, um, biology and chemistry and things like that, where you just have so many components, is very interesting in that there is truth in all of it, but
Yeah,
it somehow defies the kind of, you know, I guess notions of beauty that tie in with simplicity. You gotta, I guess, appreciate it for its complexity's sake, and
yeah,
that's really
yeah,
annoying some days, you know, like
yeah. um, yeah, I mean, yeah. Please go on. Sorry.
oh, no, no, no. I was just like, because I was just reflecting on my own journey through neuroscience, where like I started off with trying to build these simple models for neurons, and then you scale them up to going the other way and saying, what if a neuron can do 1,000 different things, you know?
Yeah,
And the truth is somewhere in the middle, and it's messy, and not every neuron is
yeah,
the same, not
yeah,
every synapse is the same. So when you try and like use mathematics, which is a language that's built on axiomatic rules, and human, you know, working memory holds maybe 10 objects in your head at the same time, it becomes really hard to distinguish whether your model is wrong,
yeah,
or or it's just the truth, and you don't have a big enough brain to hold that truth. And
yeah,
I continue to find that a very fascinating philosophical question. Like, can, like, the 11 billion ish human brains on the planet sit down together and understand one human brain? Is that like, how much compute do you need? Is this the right way of thinking about it? How many things do you need to hold for a theory of everything in your head? Like, how many variables would it have? Do you need to understand thousand dimensional space and its
Yeah.
topology to really appreciate the truth? Or can we get away with the usual low dimensional, five variables with three of them sparsely connected to each other kind of thing? Like, how
Oh,
much can you simplify this?
yeah.
And are we fooling ourselves with a lot of these truths, scientifically speaking, by just saying, hey, this is beautiful enough and it explains enough, so this is the truth? Or is it that, there's more to all of it?
Yeah.
I don't know.
Yeah. Yeah. I think. Wow, that's a really deep sort of train of thought that you've introduced there. So I'll just sort of recuperate because I got confused myself. But
Sorry.
towards the no, so I'll just recuperate for myself. Is that what you're essentially asking is how much compute do we need to understand our own brains, considering the models we already have? Or is it
Right.
that the models will never be able to fundamentally capture the kind of dynamics that exist in the human brain? I think that's essentially.
Yeah, that's one way to put it. Yeah, like I guess the folks right now who are trying to understand how these LLMs work and so on are basically dealing with a white box that has latent spaces of thousands and now millions of dimensions, right? And we are using other LLMs, computers, and whatever tools we have at our disposal to try and understand and make some sense of it. So at the
Yeah.
end of the day, as someone that had hoped that we'd have like proofs and theorems and whatnot in all of these spaces, you'd have like a computational definition for semantics, for things like that.
Yeah.
I don't know. It feels so far off
Yeah.
that I, it yeah, I don't know. Um, I don't know if we'll get there. Is what I'm.
Could you talk more about like this particular aspect about the computational definition of semantics? Like, could you?
Yeah, right. Like, so, I mean, specifically in the neuroscience context, and our lab thinks a lot about this as well. Like, when you say that you and I see an object, we perceive this object and it has certain properties, it moves from left to right, or whatever it does. Um, for us to understand what that entails, what we end up doing is that we have certain ideas and notions about what an object is. We then try and map it onto neural circuits, or you look at a neural circuit that seems to correlate with detecting an object, and then you try and reverse engineer what it's doing. But all of that is still limited by our imagination.
Yes.
Because there's no clear goal here, you don't really know where the end of all of this is.
Yes.
If you, let's say you reach the end of your imagination, let's say we reach the end of all our collective imaginations, that's what I kind of sort of maybe concerned about, let's say, then you have a certain idea about this like really complex thing, and you don't know if you should be digging deeper into specific details like,
Yeah.
oh, why is this extra connection here? I don't know what it does. You could declare it's useless, or you could say, hey, this is really important. So it's like in physics, for example, you may have data to contradict your model, but it becomes harder to collect that data if you don't have a definition for object. You don't have a definition for the big one, consciousness. Like, how do you know? How do you know anything?
Exactly. Exactly. Yeah. Yeah. So this reminds me of two things. Sorry, were you saying something?
No,
Like,
no.
oh, okay. So this reminds me of two things. For the semantics part, um, you know, Noam Chomsky, he came up with this theory of generative grammar that you can't just simply teach
Yeah.
a child to regurgitate things. Like, that's not the extent of language acquisition. It's not concerned primarily with just regurgitating, like, okay, there goes a car, and then the child just starts saying, okay, that's a car. It's like, and I think maybe he came up with the theory, or someone else did, that languages across the world share a very similar structure, in the sense that language acquisition in that sense shares a similar dynamical structure, in the sense that people, children, when they're growing up, they're able to acquire language in a way that cannot be explained simply using like simple reinforcement learning methods, like how you would, like if you were to simulate the same using like multi-agent robot systems, you probably won't be able to do it. So there's a missing, I wouldn't say variable, but a missing form of learning that we have been unable to capture using either neuroscience or theories of learning, like learning algorithms in computer science. So I think and with respect to the second thing, obviously the thing about consciousness, there's the hard problem of consciousness and the hard problem of matter, where you're like, okay, if everything you're sort of experiencing has the meaning assigned to it by the consciousness, and we don't know if the consciousness is material or not, then like how do you ascribe meaning to the thing that's ascribing meaning to everything else?
Yeah.
So
Yeah.
so I think there are a lot of um, I wouldn't say they're hidden variables, because that would like obviously be cultural appropriation with respect to quantum physics. But I think there are a lot of mechanisms that are yet to be discovered, and I think until we discover those mechanisms, I think it's like a moot conversation where we're just trying to sort of we're really sort of wreaking havoc on our brains, but we're not able to get to any sort of conclusion about what might be the best way forward with respect to the debate about, okay, do we need more compute, or do we just need to keep modeling it with like a more brute force approach? So
Right.
I think there are a lot of things that have not been given enough scientific um, treatment, like a rigorous scientific treatment. For example, I feel like the kind of things that Noam Chomsky researched about with respect to language acquisition, and also his seminal work in 1959. So I'll just give a little bit of a sort of background on that. So there was this guy called B.F. Skinner who sort of made this particular train of thought in psychology very popular, which was behaviorism. And obviously, I'm not saying this for you. I'm just saying that in
No,
case,
no, no.
like, yeah,
Please
yeah,
continue.
in,
Yeah,
yeah,
yeah.
yeah.
Please.
So his argument was that, okay, humans are just basically like very simple systems. You just have to train them like you would train neural networks. Okay, using reinforcement learning, that using operant conditioning, you can just train a child to do math or do English, or basically manipulate them using either positive reinforcement like doggy biscuits, like, okay, you get a reward, you
Yeah.
get a gold star today, or using negative reinforcement, like a beating with a stick, like basically your average carrot and stick mentality. um, but with respect to, and that got, I think this was popularized around the early 1910s or 1930s. I can't really remember. I do know that the same set of psychological ideologies was like used by Nazi doctors in their scandals in the concentration camps. So it was quite infamous, but people still fail to sort of understand that this is actually a failed model. and and the reason I call this a failed model is because in 1959, so Noam Chomsky gave like a very, like a refined critique of, B.F. Skinner's theory, which was that, okay, Skinner says that you can just train a child to acquire language with respect to, by doing so and so, blah, 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 operant conditioning, right? You
Yeah.
positively reinforce them or negatively reinforce them, and the child will be able to learn. But then he came up with the idea of generative grammar, that look, children are able to structure language in ways that have not been taught to them. So there's some kind of language acquisition happening that you're not able to account for just by just using simple operant conditioning or reinforcement learning techniques. And obviously I'm not very well versed with that work myself, so I'm able to give like a very crude and perhaps a not very respectful analysis of the same. But it was a big thing basically, and people still fail to see that we still haven't moved past reinforcement, like methods that just employ plain reinforcement learning to to model human behavior. So they're still very stuck on behaviorism. In fact, I think I remember. Yeah, sorry.
No, 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 no. Please
Yeah.
continue. Yeah.
Oh no, I was just adding like a last note, which was that I think in one of Noam Chomsky's seminars, he said that behaviorism cannot die no matter how many times it gets refuted, like scientifically, it just won't die.
Yeah,
So,
no, no, of course. I think all of this also touches on sort of the psychological aspects of doing science, especially in a field which has very few, things that are actually known. In
yeah,
some ways, like as you know, I've also been studying fruit flies. A lot of experimentalists will focus on the behavior of the animal and sort of reduce the
yeah,
complexity of the brain of the fly to the observed behaviors. So,
yeah,
like, if tomorrow you discover a new behavior, suddenly the fly is smarter than we thought. Otherwise, it wasn't. So there's no, it
yeah,
becomes this sort of reductionist
yes,
view of these things. And if, as
yes,
you said, touching on the generative side of these things, if you have a generally intelligent system, whatever that means, maybe you have a certain computational class to which it's restricted, it's still something that can traverse that entire space. So to say
yeah,
that it can only move its leg up and down because that's all it can do is I don't know, like, so then there's nothing to do on the theory side of things, then there's nothing to
yes,
postulate about. So
yes,
yeah, our lab tries to sort of definitely refute that. And you could use sort of a philosophical Rene Descartes style, I think,
yeah.
therefore I am kind of argument, of course, but you know yeah,
Yeah.
yeah.
Yeah, thank you for that. I'm very grateful that you sort of added this to that. I didn't think along these lines before, and it was quite insightful with respect to with respect to the René Descartes thing. I think it was Chomsky who said, like, if free will didn't exist, then what's the point of questioning if whether free will exists? Like, why are we
Yeah,
even
yeah.
having this conversation?
No, absolutely. Absolutely. Yeah.
So yeah, yeah, yeah. Please go on.
Oh, no, no. I also made me think of like this really, really, I think both funny but profound explanation for life, which is that the existence of life is tautological. Like there's all this like conversation about how did life originate, this and that, la la la. But like in some sense, life exists because it exists, in the sense that if it did not exist, it would not replicate, it would not exist for us to have this conversation about it.
Yeah,
So in some
yeah,
ways, just the existence of life is the explanation. Like these kind of things become tautological and circular
yeah,
in a way, because you don't have another reference point as well, right?
yeah,
Like there's no but
yeah, 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 yeah. Yeah, I mean, I think like so. I think what you've raised here is like a very simple way to sort of refute the question that there is no meaning to life. Because if there were no meaning to life, life wouldn't have existed in the sense that, there's something that has kept it going. I don't think I'm able to sort of articulate myself very clearly, but the point
yeah,
that I'm trying to hint at is the kind of question that if free will didn't exist, then what was the
how
point
would
of
you
even having? Yeah, how would you
yeah,
have this line of reasoning in the first
right,
place of questioning this sort of concept that free will doesn't exist?
sure,
Um,
yeah.
so it's quite convoluted and
It
like
is, yeah, yeah. And that's the thing, like I feel like with our capitalistic world, with ROIs being the key metric, it becomes difficult to kind of just say, hey, we don't know things. And then, I can go on a rant about the academic culture these days, but like that's a different conversation. But yeah,
no, but no, I mean, um, I do agree with that. Like, I don't want to sidetrack that entirely because one of my biggest complaints during undergrad was that engineering seemed to be a bit too motivated by practical applications
right,
without doing the due diligence with respect to the science of it, like
yeah,
the actual process of doing the experimentation, proposing theories that might be incorrect, And I mean, at least that's what my experience was with respect to the engineering department. Um, with respect to the mechanical engineering department, I mean, I'm not, criticizing them, but I'm just saying that I did sort of notice this
Yeah.
sort of
Yeah.
lack of a general thirst to to produce new knowledge
No,
and fill in the gaps.
I hear you. Like I've thought a lot about this because what got me interested in engineering was just clever ideas. I
Yeah,
didn't even I
yeah,
just you look at something, you're like, how did you come up with this? Like
exactly.
what made you think you put these right? And there was that joy to it. But then
Yeah,
I think going through undergrad, of course, because you only have 4 years to take in a
yeah,
field that is hundreds of years old, they kind of tell you what the cutting edge is, what the
yeah.
basics are. There's no like
In
rhyme or
between.
reason, right? And
Yeah,
and on the other side, though, like on a more serious sort of research note to the same thing, is that only ideas that are feasible in the next 5 years get funded these days. Like,
yeah,
there's no
yeah,
space to sit around like maybe Tesla did with a random coil and just, run electricity through it and see what happens. I love that kind of like
yeah,
research, and there's
yeah,
still pockets of science that let you do it, but, by and large,
yeah. Yeah, that's quite true. Yeah, I mean, yeah, it is unfortunate. It is unfortunate.
yeah, it's tricky though. You can't discount existing knowledge, which keeps
Yeah,
compounding year on year. So, but yeah,
yeah. That is unfortunate, but hopefully we can have like another podcast episode to like discuss all of that stuff.
yeah,
I'd love
I
to.
look
I'd love
forward
to.
to.
Yeah, I'd love to invite you like right now for like another episode and just discussing this particular thing.
Yeah, I'd be
Where
happy to.
I'll send you the formal invitation soon. All right. So, moving on to the next question. Can you share like specific challenges where like you've mentioned just now in like the engineering part of it where you were like, oh, this was like really witty, how did you come up with it? So like, can you
Yeah.
share like specific challenges where creative thinking was essential to overcoming the same set of challenges, and what valuable lessons were you able to learn from this experience about, I mean, creativity in general is quite generative. So,
Yeah.
like, what was there like a mental blockade that you were sort of able to, remove from your point, like vantage point, and then you were like sort of had like a clearer understanding of sort of how to think?
Yeah, no, I had to give this a fair bit of thought, and I might give a Zen master kind of
Please,
answer, a meta
yeah,
answer here.
please, please.
But, like, I think when people describe creativity to kids, the first, saying is think outside of the box.
Yeah.
But if you think about just that saying, you still have to define a box to be able to think outside of it, right? Like,
Yes.
so what I've learned, especially in neuroscience, where like we've been discussing so much is unknown, sometimes constraints are the best thing you can do for your own creativity. Like by adding more constraints, you may actually end up being more creative in the clever sense of actually solving the problem. So what I mean is sometimes, I'm trying to model, let's say, how C. elegans, which is this simple worm, how it does chemotaxis, which is where it can move towards the source of a chemical. Now, if you don't throw in any assumptions like, okay, it has a limited number of neurons and these neurons are not magic and so on, you can go on this sort of almost unconstrained search through solution space. And that is creative onto itself. But in some ways, there's no end to that. But instead, if you constrain yourself to saying, okay, I will constrain my models to neurons that can actually be built in silicon today, it leads to solutions that are creative in the, hey, I solved a clever problem kind of sense. And I've encountered this problem perhaps with my own problem solving approach many times, where I am so fixated on sometimes the big picture of like, oh, but we also know this fact about neurons or that fact about brains, which is not accounted in my current model. It takes me out of that zone of actually solving something to begin with. And I think that's the Zen wisdom that physicists are both, derided for, but sometimes cows need to be spherical, like it is just what it is. And the, yeah,
Yeah.
the art is in picking when, like
Yeah.
not too early and not too soon in that process. Yeah. So I mean, that brings me to the point of saying that also it's okay to make assumptions and simplifications. The art is in knowing when, and
Yeah.
sometimes you also have to give up on the hope of finding an answer, and maybe the creativity lies in asking those questions
Yeah.
themselves. Like you
Yeah.
can, those are two sort of orthogonal axes. Sometimes you
Yeah.
can.
Yeah,
So
yeah, yeah, yeah. Absolutely. So like, between exploring new stuff and exploiting what you already have and sort
right.
of building up on that, yeah, that's completely, yeah, completely
Yeah.
agree on that. Yeah, I mean, I think it's also kind of circular that once you
Hmm.
go about exploring, you gain new knowledge, accumulate new knowledge about maybe how to solve existing systems. Like there's so many fields where interdisciplinary, explorations can actually lead to innovations that wouldn't have been imaginable before, going on that interdisciplinary excursion.
No, absolutely. Yeah, it's definitely, a gamble, and you have to have your own take on your risk aversion, risk
Yeah,
tolerance, so to
yeah,
speak. It just becomes interesting when you're doing this in theory space, because you can
yeah,
build on pillars of sand to
yeah.
build bigger pillars of sand. So we've got to be careful. But I also did want to maybe give a specific example of this from
Please.
my research where, I could talk about certain neural circuits that I've designed and so on, but I rather wanted to sort of talk about the connectome again, because maybe you can leave a link to an app that
Of
our
course,
lab uses to
of
visualize
course,
it.
definitely.
So yeah, basically our lab also does a lot of like web design, web development on the side, just because this 3D connectome data is so complicated to explore. So you could start off your scientific process by really seriously thinking about exploring the connectome, and I'm sorry, explaining the connectome's function. Or you could simplify it and say, okay, hey, I admit I don't know what the hell is going on here. I'm just going to build tools to explore this 3D data more efficiently. And it turns out on that journey, I found that you also then end up, as you said, circling back to function as you explore these things. So there have been a lot of like creative challenges with just visualizing complex 3D data with neurons all intermeshed together. On a 2D screen, you don't really perceive which neurons are properly connected to others. Just it's like 100 trees all got mushed into each other.
Yeah,
So the
yeah,
branches
yeah,
are really hard to tell apart.
yeah.
So we've been building tools to untangle that. I've explored hyper, let's say, um, hyperbolic space embeddings. I've explored sort of VR apps, sort of looking at tree structure topologies of the neurons. So just that creative process of exploration became that much more fun as well by forgetting about function for a bit. And then, as you said, you can come back to it once you've collected more data by just visualizing and exploring the data. So there's something to be said about just learning by osmosis. You just
Yes.
immerse yourself in something and see what pops out. So
Yeah, 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 yeah. Yeah, 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 yeah. Yeah, I mean, yeah. Yeah, I think
sorry if
that's
that was too
this.
much.
No. It wasn't too much. It was just, it's it definitely wasn't too much. That's not why I paused. I paused because I'm, trying to reconcile the gap that we still haven't discovered, the sweet spot between exploration and sort of just mulling over the things that you already know and then applying
Right.
those.
No, no.
So yeah, so I think that's like that's probably a 2 hour podcast in itself.
Yeah, no, I actually love this topic because if you look at how science is taught to folks, that sense of just like, I don't know, the unknown is
Yeah.
lost when you teach it so matter of fact. Like with the laws
Yes.
of physics, for
Yes.
example, it's like, oh, Newton just
Yeah.
discovered the laws. This is what it is. It's like nothing came before or
Yeah.
after. Oh
Exactly.
man, like. I, so yeah, and that's the funny thing, like even with neuroscience, maybe in 100 years we discover so much about the brain. A lot of these conversations that we're having today about what we don't know, a lot of human creativity actually gets buried
Yes.
in the history of these things, like
Absolutely.
because it's today two ideas are equally valid and equally creative. It's just that the truth is one of them, you know,
Yeah.
and those get forgotten. Um, yeah.
That is very true. That is so true. No, that is, I think that really hinders the process of critical thinking and critical
Yeah.
questioning.
No, absolutely does, right? And we end up hoping for normative and prescriptive answers to questions that may require centuries of just
Yes.
sitting around saying, I don't know, you know,
Yeah,
like,
exactly.
so it's, yeah, again, like back to sort of the ROI thing. There's no
Yeah,
ROI on curiosity in the short term. I don't,
absolutely.
yeah.
Absolutely. Yeah. No, absolutely. No, I think there was someone who I can't remember who said it. I'm forgetting who said it, but I think the number one question that makes you competent as a researcher or as a scientist is the statement I don't know. Like that's what makes it.
No, absolutely. And I think I'm grateful to some of my mentors as well for like early on sort of also putting up their hands and saying,
Yeah.
I don't know, we're just trying to do the best we can. This is, yeah, I think we need more of that in school as well, you know, like
Yeah,
you know,
absolutely.
there's always a curious kid who asks, but what if, you know, an atom was a watermelon? Fine.
Yeah,
What if it is, you know, like,
exactly, exactly.
yeah.
Yeah, yeah, and it's usually those kids who are like, they're not given that much sort of like those kinds of questions. They're not
Yeah.
given the kind of respect that you would expect. I think, yeah, I think it was Carl Sagan who said like if
Ah,
the
yeah, for sure.
yeah, yeah, I think it was on some talk show that he said that okay, if your kid asks why is the moon not green and it's why is it white instead of green, or
Uh-huh.
why is the moon circular, like
Right.
what?
Yeah.
So like those kinds of questions are really what sort of that's actually the more sophisticated way of doing science rather than yeah, the moon is circular,
Right.
it has got gravitational forces, blah 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 blah, and it's just you don't
Yeah.
really get a lot from that.
No,
Uh,
absolutely. I know what you mean.
and I think it discourages a lot of people from doing science as well, especially in the Indian
No,
education system.
very much so, very much so. I find that to be a tragedy, and we were talking a little bit about, you know, our experiences at college as well. Some of the smartest people I know may not feel as encouraged to explore their own ideas because everything is so optimized for certain things in our society, and I just think we're in the 21st century. We
Yeah.
can produce enough food for everyone and so on. I, you know, maybe it's time we just sit back and think again. Like, what do we
Yeah.
want to do from this point on? Like, so yeah,
Yeah. It's quite unfortunate.
of course.
But yes, we will discuss this on the next. No, I'm definitely inviting you for another podcast episode. All right. So moving ahead, can you share an experience that solidified your commitment to mastering your research area?
Yeah, I would have to say spectacular failures and a series of those failures, like
Yeah.
where I was doing my master's thesis on trying to model how brains could do probabilistic inference,
Ah,
specifically Bayesian inference.
basic. Yeah.
So you would so I was looking at like these probabilistic graphical models, trying to map them onto circuits of neurons. You have different sampling schemes. I was trying to reconcile what's called Gibbs sampling and message passing together. La la la, a bunch of things happen. You know, I throw in a bunch of assumptions, a bunch of different models. Stuff happens, right? Up until the point where, for the people who do physics, I had to renormalize the probability distribution. I couldn't design a circuit that uh, computes the renormalization factor for the entire probability distribution. So my entire model was not useless, but it fell apart or it fell short of what I wanted it to do. And then banging my head against a wall trying to fix that led me on so many different, journeys of through both computer science, neuroscience, and a bunch of other things that it got me thinking about just how many different solutions there can be to a given problem.
Yeah.
That got me so committed to just continuing this journey. Like
Yeah.
maybe there is a payoff. Maybe as these, you know, failures accumulate over the years, you also hope that maybe 10 years from now, I will have enough knowledge to come back and
Yeah.
also pay back that debt to myself, you know, and it's a it's a circular form of motivation, but I
Yeah.
think it really, you know, yeah. So
Please. Yeah,
I
no,
know
please go on.
that. I was just saying that, like, yeah, the word mastery is something that, like, sort of precludes that you know what you're trying to master, which is why I can't definitely say that, like, I've mastered any specific field of neuroscience because it's all unknowns. But
Yeah,
what I'm trying to perhaps master is the the ability to maybe bring in new perspectives
yeah.
and keep going and churning out certain potential solutions to all this, because it's hard to define success with a model where someone can come up and say, hey, but it doesn't work for case
Yeah.
X Y Z W la 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 la. So
Yeah, yeah, no, yeah, I think that's quite interesting because it reminds me of this statistician George Box who said all models are wrong, but some are useful. So,
yeah,
so I think it's just about the zeal to build more sophisticated in terms of functionality, not necessarily in terms of their in terms of their structure, but like functionality and like more sophisticated to be able to capture a very a very wide range of phenomenon, like a theory of everything kind of deal. So
sure, yeah. I'm glad you brought that example up. Yeah, yeah, yeah. I think in what you said, right, like it also sort of points to mastery in terms of just accepting, first of all, that there will always be trade-offs. And the
yes,
mastery isn't recognizing those trade-offs. Even
yes,
before you do anything,
yeah,
you just know, okay, all right, I'm going down this path. It will lead to certain things, but maybe
yeah,
not to others, which is
exactly,
why, as a PhD student, I can only tell you how many times you hope your advisor and their wisdom is wrong
yeah.
in sort of shooting down certain ideas. But that's really the fun dance here of, like, saying, maybe a chess grandmaster can see 10 moves ahead, doesn't know exactly what's going to happen, but there's some kind of intuition that maybe you shouldn't move this piece this way, and it just, it's so hard to even define mastery in that sense, but it's something.
No, that's completely it, right? I think. Sorry, I usually take a long time to just like sort of think and reply.
Oh, please,
Yeah,
please,
so
please, please. I should do more of that too.
so the zeal of doing science is based on sort of trying and failing and exploring things that you didn't know before. It's like the process, it sort of encapsulates the process of learning. That
Mm,
you're looking at things that you haven't known before, that you've maybe taken for granted, and you're like,
yeah.
okay, maybe this is wrong. Maybe I need to revisit and reassess
Right.
this thing from
Right.
the scratch, from the ground up.
Yeah.
And I think because I was going to say this before, like, and because of what you've said about the Zen philosophy with respect to exploration and all of that stuff, I think the ultimate goal is, in some senses, like a true understanding of ourselves as like human beings, like enlightenment, so to say.
Yeah, no, I know what you mean. Like, it's sort of asking how much of this universe can humans even hope to comprehend. It's not about getting there. I mean, you'll get there if you get there. But yeah, yeah, like you said, yeah, I agree with that.
Yeah.
Yeah, it's interesting in the neuroscience context also, because if you knew what the limitations of the human brain in that regard are, maybe someday you could hope to move past it. Like,
Exactly.
like, it's that, I mean, this is like thousands of years into the future perhaps, but that's really the question we might be
Yeah.
faced with, right? Like,
Yeah.
if you do have knowledge of the current limitations of cognitive, let's say, I don't know, embodiment,
Yeah.
AI or otherwise, where do you go with it? Like, and
Yeah.
what values, what do you use to guide your search, right? Like, does it just become Frankenstein zoo full of like crazy creations? Like, there's no God, I don't know.
What are we even doing this for? Yeah, no, I
Yeah,
completely get, like, it's like the
right.
existential dread sort of thing, like
Yeah,
the existential angst,
yeah.
nihilism of sorts.
Yeah, yeah, no,
Yeah.
of course, right? It's hard. I mean, I find it so funny in some ways that, like, physics for the past century was so focused on like atoms and molecules and just I guess cute stuff in that way. Like it's not consequential to immediate human life. That if you take that like hypothesis seriously enough, then where does meaning actually exist becomes really like shaky. Like is it in the atoms? Like
Yeah.
what?
Yeah, it's like, is an atom sentient, for example? Like,
Yeah,
uh,
yeah, or like even in the human context, like, you know, are we just like redundant bags of protoplasm, which is
hmm, hmm.
it's how I describe people I'm angry at sometimes. Like it's uh, I don't know. We have these like value systems in place that respect human life as we should, and yet some tyrant who comes along and says no, I disagree with all of it, can go down this route of just being a I don't know scientifically driven tyrant, I guess. I don't know. So anyways, I think that's
Yeah.
a conversation for a different day, but yeah.
Yeah, no, but no, but I really appreciate that you brought that up because that reminds me of Richard Feynman and Freeman Dyson and that particular example because Dyson was quite vocal about verbalizing his sort of hesitation, or rather, a complete, he was against the use of nuclear weapons after the Second World War, right? And, oh, oops, can you hear me?
Yeah,
Sorry,
I
I
can
think
hear
it's
you. Just cut
trying,
out for
yeah,
a minute. Yeah.
yeah, there. I think it's better now.
Yeah, you're back. You're back.
Yeah,
Yeah,
okay,
yeah.
great. Yeah, okay.
Mm-hmm.
You can hear me completely fine. It's
I can.
completely.
All
Yeah,
good.
okay, great.
All good.
Yeah. So the thing that I was talking about was I really appreciate that you brought that up because there was this example of Richard Feynman and Freeman Dyson. Because after the Second World War, Feynman went into depression because of what they had created, like with respect to the atomic bomb. And Dyson was extremely vocal about this with respect to speaking out about doing responsible science
Mm.
for the world. Like you can't just be like, okay, yeah, science cannot be limited to just, yeah, we can build it, so let's just build it. It has to be.
Yeah. No,
It ha-
absolutely, right? Like,
yeah,
I think the flip side of nihilism on a sort of positive existentialist note is that if something isn't broken and it's a valid thing that can exist, let it exist. Like
yeah,
why do you need to go ahead and destroy it? Like it's
yeah,
not that you have a value system that tells you something that's better, right? Like if everything doesn't mean anything to you,
yeah,
then let what exists be, right? Like
yeah.
let's not
Exactly.
uh,
Yeah,
yeah,
yeah. Yeah, but let's definitely talk about this in the next
yeah.
podcast. Okay,
Absolutely.
so, all right. So, wrapping up, would you like to, talk about this is more of like a get to know you sort of segment of the podcast where,
Sure.
like,
Yeah.
would you like to talk about your, favorite and least like subjects in school, in college, and how about now? And, what were the reasons behind them being your favorite and least liked subjects? And also, is there any inspirational statement from a mentor or teacher that motivated you in your research journey?
Yeah, right. So, yeah, when it comes to school, early on, or maybe, I mean, okay, for all of school, my favorite subject, if you want to call it that, was like the physical training period, just like running around like a madman on the ground. Nothing beats that, I think, But when it comes to more sort of, let's say, academically oriented subjects, I liked English and history the most because in all of science, math, whatever, the underlying thing that I personally am just passionate about overall is storytelling. I just love stories. I think humans are storytellers, and the rest is just details, and we can convince ourselves that we're smart or not or whatever. It doesn't matter. So I loved English and history a lot. I didn't like subjects like geography and maybe a bit of civics, which had a lot of facts, and you had to remember the facts and then regurgitate them. I still enjoyed learning all of it, but passionate not so much perhaps. And I had the same crib about chemistry and maybe bits of physics as well. There was, as we were discussing before, no room to ask like
Yeah,
how or why.
yeah,
Especially with chemistry, I was just so overwhelmed. My brain,
yeah,
I don't have the best working memory for things that are not connected. Like I can't hold 10 unrelated compounds in my head. I don't.
yeah.
Okay, you added another oxygen atom. Cool. Okay, what do I do with that? Like, so,
um, I, I think nomenclature was probably like is probably the lowest point in chemistry. Like, okay, alkane, alkene, alkyne. It's like I'm doing Sanskrit
Yeah,
again.
right.
Like I'm just doing like just gone back, and
Yeah, yeah.
and that's good. I mean, it definitely teaches you a certain sense of scientific linguistics.
Sure,
Um,
sure.
but I,
At
I
least it's
feel,
an
yeah,
attempt.
yeah, definitely. So in that respect, I really respect organic chemistry. But I feel like there are like some things, and like you said, I didn't actually think of it like this before. With respect to physics, um, I started doing physics like a couple of months in ahead of school of when school
Right.
started. So I think I had that bit of like an advantage that I'd already started questioning things
Yeah.
before the education system sort of ruined that perspective. Like it's just feeding it on. It's just sort of forcing the perspective onto you without actually letting you think.
Right.
Um, and so yeah, I definitely agree with that. That the way that physics is taught, it's not. Uh, it doesn't engage you with critical thinking. Yeah,
No,
but but
absolutely. Mhm.
but it's
Yeah, no,
really
please go ahead.
no, but it's really interesting that you liked English and and
Hmm.
history and literature. I didn't like those subjects at all. I mean, at least not with respect to. Maybe it was just that I had this blockade which you probably didn't, and which is very exciting to see that because as of now we're sort of interested in the same kind of philosophies and the same
Right.
sense of things of doing science, which is that I was never able to see English as a medium to sort of think critically,
Right.
but which I'm able to do now,
Right.
but I
Right.
wasn't able to do then. So it's really interesting to see that kind of
Yeah.
where we're coming from. It's
No,
being
no,
so
no.
different, but we've sort of converged to the same direction. So
Yeah.
yeah, please go on.
No, absolutely, I agree. I mean, I think with regards to like even math and science, physics, chemistry, and all of that, like I grew up going to a library sort of every weekend, and so I was reading a lot of science on the side, and I was kind of always sort of in my own world in school, not so concerned about what someone's teaching me as much as what I could potentially learn. So I loved English and history just because maybe I wasn't, there's no limit to exploring literature, of course. And I love that, like, at least you'd get to, sit up and explain your interpretation, and it would be taken as a valid form of exploration instead of like, oh, yeah, you can't even ask, as you said, why the moon is potentially green. So I love that. And, like, with regards to chemistry, I think as I've matured more now, I've sort of seen what I thought previously is very frustrating, where when you're studying organic chemistry and they're trying to explain the mechanisms of a bond breaking and connecting again, there would always be 10 different exceptions. And it was sort of so heartbreaking. You worked so hard to understand the mechanisms, and then the truth is that, oops, hey, nope, that's not what it is. So I think if explained correctly, that would sort of make for more mature scientific thinking, which is to say that, yeah, this is probably the best you can hope for with a model, with a theory. But it wasn't taught that way, so you had the wrong idea.
Yeah, no, completely agree on that. I mean, yeah, you brought this point up, which I didn't think about before. Like, with respect to literature, you can, first of all, there was no hierarchy. Like, you can read any chapter that you want. You didn't have to, like, oh no, you have to do kinematics first, and then you have to do rigid body dynamics. You can't do like one way or the other. So
Right.
I think that sense of sort of exploratory freedom, and even with respect to chemistry, like you said that there are like 10 different exceptions. Like there's just one rule, there are like two elements of the periodic table which follow it, the rest 118 are exceptions.
Right. Yeah.
so, so yeah, I mean, um, I think historically scientists have relied upon categorization and classification as a means to maybe preserve knowledge or memorize knowledge in ways that maybe aren't exactly conducive to critical thinking, but
Right.
and they would have had their own reasons for developing those methods. But from this discussion, what I'm able to conclude is that maybe we need new methods of being able to store knowledge or to inquire about knowledge that differ from the previous techniques and maybe might give us an advantage over how we process information in the first place.
Yeah. No, that
Yeah.
makes sense. And I would say, like, at least the attempt that I appreciated with our textbooks at the time was like those extra boxes
Yeah.
with like some stories. Like I just would want people who are like getting into any field to be on their toes, like, because that is the other side of curiosity, right? Like, what are you excited about if you don't have hope to encounter the unknown, right? Like, if it's so, maybe a bit more of that. Like with math, for example, no one, I mean, I learned later that, like, if you challenge one of Euclid's axioms, you would get entirely different topologies for space itself, right? Like these kinds of just what if questions, I think, really should, be baked into our system for sure.
Yeah, yeah, no, that is so true. I mean, with respect to the Euclidean geometry, like you're just given, yeah,
Yeah,
this is like the corner of a room, and this is how you represent with like three axes,
right.
but but like you get to discover later, oh, okay, maybe everything is not Euclid, maybe all kinds of geometries are not Euclidean, and they're like
Yeah.
these metric spaces and whatnot, and so yeah. It's it's very weird, like the way that concepts are just sort of fed to you in a matter of factly way rather than having uh, you know
Yeah.
uh, sort of propagating them as ideas rather than just facts that okay, this is one
Yeah.
way we could model the world. It's not the only way, but
Yeah.
this is what we're going to study. But no, this is the only way we can model the world, and there's nothing outside of this. So,
Yeah.
so I think that's the box that and even within that, they're like it's like a Russian doll with like you just keep going and they keep restricting you. But yeah, yeah, but but okay, so this was basically it. Is there anything else that you'd like to add with respect to mentorship and like? So,
Yeah. Yeah, sure. So I'll just say something related to all of this because up until maybe like grad school research, there was a lot of the same kind of normative teaching that goes on in undergrad courses as well. And I think one reason is just that a dialogue requires, say, a smaller scale of the classes as well, and time and all of that. And like when you have, say, 50 or 100 students, the best you can do is shout and just say, hey, this is what it is, figure it out, la la la. I think in grad school, I was really happy that my advisor, or Elazar, in our lab at Columbia also is someone that is very, how would I say it? He's not religiously bound to existing ideas. Let me put it that way. Very questioning of everything. And I like what he said once, which is that if you're not insecure about the research that you're doing, you're probably not doing research proper, And so I think to encourage the being comfortable with the unknowns from an earlier age and to just sort of accept that, hey, we're just humans that evolved from monkeys, that evolved from something else. We're trying to do the best. There's no absolute truth,
yeah,
and maybe we won't find an absolute truth, and we
yeah,
have to make peace with it. I think it'll make for better human beings as well. Like that's what I feel.
yeah. So addressing two things, like I'll just address the first things that comes to my mind first. Like with respect to the thing that you just said, my advisor at Imperial also said this to me, which I'm quite grateful about because he said that okay, we're trying to do this method and trying to see if it works. But if it doesn't work, that's going to be a scientific achievement or an establishment in itself that hey, you can't
Right.
use this method for this thing. So it's like people instead of looking at science as playing with toys, okay, maybe this circle does not fit into the square and you're trying to put it in but it doesn't fit. Instead of looking at it like that, they're just looking at results, like results driven approaches where you're just trying
Yes.
to put the star into like a cylindrical column and you're just not able to do so. And I think science is a lot more, if in the education system, science is just taught with respect to a lot more playfulness. That, okay, yeah, let's just explore this. Like
Yeah.
let's just discover something new. I think that really makes a big difference. With respect to the other thing that you said, that the scale of the classroom, I couldn't agree more with respect to that, because once you have sciences, whenever you're learning a new topic, it's not just about science. It's about the scientific method to be
Yep.
learning anything,
Yep.
there has to be discourse, there has to be disagreement that, okay, my idea about this is, the following. Like, this is how I conceptualize this particular mechanism
Right.
to work.
Right.
And then let's say you're the expert in neuroscience, and then I give sort of state that as my argument to you in the classroom, and then you're like, okay, let's discuss that, rather than, obviously, if you're like in a classroom with hundreds of people, like 50 or 100 people, you'll be like, I don't have time to sort of do this with every single person. And and whilst I understand that, I think it's quite, it doesn't, I think it disrespects both the teacher and the student.
Yeah.
um,
Yeah. It's
like it's,
unfortunate.
yeah, it's quite unfortunate, and it's not sort of giving the space or the platform to engage in the kind of discourse that would give rise to the development of critical thinking. So I think that's or that playfulness, right? Like, okay, let's
Yeah.
discover something new. So yeah.
No, I absolutely agree. Like, I feel like, just to say one more thing along
Yeah,
these
please.
lines, I find it very surprising, or I did find it very surprising that the 4 years of undergrad that I experienced, or five, let's say, with the masters and all of it involved such like so many lectures that were just about transferring information.
Yeah.
And I just, it just continues to blow my mind that we haven't reformed our education system, and maybe now's the right time with all of these like AI tools, even if they're not like all that useful to synthesize new knowledge, they are great at cataloging existing knowledge. I think it would be a very interesting experiment to just provide the syllabus to students, let them like explore it on their own, at least in some classes, let's say, and then you come to class to just discuss questions that you have and make just more time for all of that. I have attended some of those classes in grad school. It's just so much more fun. I think undergrads are smart enough to sort of do that as well, like it's yeah.
Yeah, definitely. No, I mean, I think, no, I completely agree with that, because I think a lot of people just have this fear, like you said about that guy, right? Who's in the classroom, who's asking
Right.
that particular question to the teacher, and everyone else is sort of shaming that person
Yeah.
to not ask, and then everyone
Yeah.
has this, like,
Yeah.
real fear that, yeah, angst that, okay, maybe I shouldn't, maybe this is a stupid question, maybe others will laugh at me. So
Right.
I think we have a long way to go with respect to that, and
Very
I think
much
we should really do that.
yeah. It'd be so much more fun,
Yeah,
less stress for
absolutely.
everyone as well. Yeah.
Absolutely, yeah. So I'm really grateful for this, really grateful
Thank
for
you for
this,
having me,
yeah, for having you on my podcast. I'm really grateful that you were able to take time out. Um, and is there anything else is there anything that I haven't asked you that you would like? Oh God, that is unfortunate.
No
Am I
worries.
back? Yeah, I think
I
we'll
can
just,
still hear you.
yeah. You can still hear me?
Yeah,
Am I
all is
back?
well again.
Okay.
All is
All
well.
right.
Yeah.
Okay. So, are there any things that you'd like to add, or is there anything that I haven't asked you that you're thinking about and that you'd like to get it out there?
Yeah, no, I just wanted to thank you again for inviting me to the podcast.
Okay.
It's been so much fun, and I've really enjoyed our conversation. And like we were saying, there are quite a few other threads that sort of may not be on the same sort of scientific plane, but more on sort of philosophical
Yeah.
and let's say socio-political
Yeah.
threads. And I'd love to explore all of that with you.
Absolutely.
I
Absolutely.
don't think these are disjoint
Oh,
as
no.
much as people would like to believe, and so
Yeah.
it'd be very interesting to talk about all that stuff.
Absolutely. Oh no, I'm sending you an invitation right after this. I'm just thinking about what to write in the overleaf document, so I'll just send it to you after this, and we can set up a time at your convenience.
Sounds
Yeah.
good.
Yeah. So, I'm really, thank you so much for coming
Thank you
on
again
the
for having me,
podcast.
Arush.
Yeah.
Yeah.
So I'll just stop the recording now.
Yes.
Yeah.
Okay.
All
Sounds
right.
good.
Yeah.